If forever chemicals transform inside us, how can we ever trace their true origins? You know how some problems feel too vast to truly grasp? PFAS, those forever chemicals, now found in virtually every living thing, can certainly feel that way. This piece doesn't just remind us of their omnipresence and risks, but invites us into the intricate detective work scientists are doing. They're trying to read the fingerprints these chemicals leave in our blood, grappling with how they transform and accumulate, making the task of tracing their origins incredibly complex. It's a fascinating look at a deeply personal and global challenge. Written by Carrie McDonough, Associate Professor of Chemistry, Carnegie Mellon University, in The Conversation. Narrated for Arva. Virtually every living thing on Earth, from Patagonian penguins to newborn human babies, has been touched by the synthetic chemicals known as per- and polyfluoroalkyl substances, or PFAS. In fact, you would be hard-pressed to find a sample of human blood, tissue, or breast milk without detectable levels of at least one type of PFAS. Making matters worse, researchers are continually uncovering links between human exposure to PFAS and poor health outcomes, including a weakened immune system, a heightened risk of kidney and testicular cancer, and pregnancy complications, including preeclampsia and reduced birth weight. The levels of some PFAS considered safe in U.S. drinking water are decreasing. Despite this, the Trump administration is in the process of revoking and possibly rewriting proposed regulations for all but PFOA and PFOS, two of the most commonly used PFAS until the early 2000s. U.S. maximum contaminant level goals for PFOA and PFOS are 0 parts per trillion, meaning there are no levels the U.S. Environmental Protection Agency considers safe. Meanwhile, thousands of PFAS have not been studied and have no regulation or oversight. In many cases, there is no monitoring data on their presence in consumer products, water, and food. As an expert in chemical pollution, I have studied a wide range of synthetic and natural chemicals that can have harmful health effects for humans and wildlife. A major focus of my current research is tracing PFAS from their initial source, including consumer products, contaminated food and water, and the air, to their resulting fingerprint in an organism's blood and tissues. By following the journey of how PFAS move into the bodies of living things, including people, scientists like me are working to improve safety recommendations and usage guidelines for these chemicals. First, though, we need to understand how these complex chemical mixtures are transformed as they accumulate in the body. What are PFAS? PFAS are a large class of organic chemicals, meaning molecules that contain carbon atoms, that have fluorine atoms added to them. This fluorination allows PFAS to aggregate on surfaces in ways that are desirable for many applications. For example, PFAS are used in nonstick cookware, food packaging, cosmetics, textiles, and even toilet paper, among many other commercial and industrial products. They're also heavily used in semiconductor manufacturing and lithium-ion batteries. PFAS are commonly called forever chemicals because of their astonishing persistence. Due to the strong chemical bonds between carbon and fluorine, they don't break down easily. This durability is desirable for manufacturers, as materials made with PFAS can function for a long time without degrading. However, persistence becomes problematic when PFAS leach or evaporate out of products and into the surrounding environment. PFAS can remain in drinking water sources and in sediment for decades to centuries. If dissolved in water or released into the air, PFAS can also travel long distances from their point of origin, ending up in remote locations. For example, PFAS initially released from industrial regions can end up in the blood of white sharks in the Atlantic Ocean or in Arctic environments. PFAS fingerprints. What happens when PFAS are absorbed and accumulate in the body? When someone is exposed to PFAS, it leaves a unique pattern of chemical contamination, what researchers call a PFAS fingerprint, in their blood. Studying these PFAS fingerprints enables scientists to learn about sources of PFAS exposure and how they differ among people who live in different places, have different jobs, and use different products, among other factors. But to be able to use these PFAS fingerprints, researchers first need to understand how specific exposures contribute to someone's PFAS fingerprint over time. The composition of this fingerprint is different from the mixture of chemicals someone was initially exposed to, as some PFAS accumulate in blood to a greater extent than others. Without understanding how a PFAS mixture is distorted and changed in the body, it's very difficult to know what sources were major contributors to a person's lifelong PFAS exposure. For example, firefighters and military service members use aqueous film-forming foams that contain hundreds of poorly studied PFAS. These are soapy, sudsy materials that form a film over fire and starve it of oxygen. They're commonly used in emergencies, such as airplane crashes, train wrecks, vehicle fires, or any other fire involving fuels. Many firefighters and first responders who have used these foams are now grappling with serious health problems, including cancer, and many have wondered whether PFAS contributed to their illness.
A clearer understanding of the PFAS fingerprint that would be expected in someone's blood after years of using these foams could help determine whether they are a unique source of the PFAS accumulating in their blood. PFAS in the body. Fingerprints at the scene of a crime are often a major clue leading detectives to the perpetrator. When it comes to identifying sources of PFAS contaminating human bodies, however, researchers like me aren't always so lucky. For one, PFAS are typically present at low concentrations in the environment, but can build up to higher levels in the body. For example, people drinking water containing PFAS will typically have levels 50 to 100 times higher in their blood than were measured in the water. This is because the body's rate of PFAS uptake exceeds its rate of excretion. But not all PFAS will increase in blood to the same degree. PFAS that are more likely to bind to biological components, such as proteins and fats, will more readily accumulate in the body. As the mixture of chemicals in drinking water, for example, continues to accumulate in the body, these types of more bioaccumulative PFAS, such as PFAS, will make up a higher proportion of the fingerprint than other types. This distortion complicates my and other scientists' job, since we need to be able to predict how much each PFAS accumulates in the body to estimate how these chemicals will change in the body. On top of predicting which PFAS will accumulate in the body and which will be excreted, researchers also have to contend with a person's metabolism, the process by which chemicals, including some PFAS, are biologically transformed by the body. Although the chemical structure of PFAS may change in the body, the resulting chemical is usually still a PFAS, a highly fluorinated molecule. After entering the body, many different types of PFAS used in different products can be transformed over days to years, while the highly fluorinated backbone of the molecule remains intact. By these processes, many different PFAS eventually transform into just a few highly persistent PFAS. For example, many distinct PFAS containing a PFAS backbone can ultimately change to PFAS in the body. Once these distinct PFAS have all become the same common chemical, it may be impossible to identify how a person was initially exposed.
Protecting yourself from PFAS. Despite all the complexities of PFAS research, researchers are making progress toward better understanding how these thousands of chemicals accumulate and transform in the body. Studying real products that contain complex PFAS mixtures can help researchers get closer to finding biomarkers that can pinpoint a PFAS source in a person's blood. The most effective way to protect human health would be to cease the use of PFAS entirely in all but the most essential of products. Until then, consumers can look to resources such as those from the Green Science Policy Institute and Environmental Working Group to help them avoid PFAS in products they use. There are also a number of commercial laboratories that offer drinking water and blood testing for some common PFAS, but it's important to remember that these tests don't capture the whole picture of your PFAS fingerprint. Scientists like me are still hard at work capturing many more PFAS that have been overlooked.